Another way of achieving similar aims to find the coefficients is to use a regression type approach. And that's really appropriate when the dimension of the space is fairly large. You want a flexible sampling systems, and you want to come up with a sparse series. So you essentially go to the family of compressed sensing techniques to try to decrease the relative errors of the error norm, right? So this is a discrete error norm, okay? And you want the series to be to have as few members as possible, okay? And the beauty about this is that it has flexible sampling patterns, but it is a little bit more expensive than Galerkin because essentially the tolerance level, right, how far you are from the actual sample, requires a cross-validation. So you have to repeat the calculation until you have a good estimate of the tolerance. Okay? And the beauty of this is once you have the series, you can do a lot of things with it. For example, the mean of the series is just the zeroth coefficients, and the variance is just the sum of the squares, is the weight sum of the square of the coefficients. It decomposes very, very nicely. If you want statistics on the output, then you're really integrating with respect to psi. It's easy to integrate a series. You have to integrate the basis functions. Okay. And if you want to differentiate with respect to psi, to do the adjoint, for example, you just differentiate the basis functions. Beautiful, because we know how to manipulate a series. Okay. That's the real beauties of polynomial chaos techniques. Okay. All right. So for our cases, most of the time we're going to use input density functions that are uniforms, in which case the basis functions are essentially Legendre polynomials. And in the multidimensional case, they're Legendre polynomials in their product of Legendre polynomials, tensor products. Okay. All right, so that's in a nutshell my take on polynomial chaos. Okay. So let's go back to our problem and let's try to identify conditions under which we can find these uncertain inputs that describe the uncertainties. And you've heard this many times before. Essentially, we resort to a singular value decomposition. I don't want to perturb every single value of the model parameters independently. Actually, that doesn't make sense because these variables are linked by dynamical laws, and those have to be respected. Okay. So what we're going to do is essentially an empirical orthogonal functions decomposition, principal component analysis, in order to do this. And the way we're going to do it is we're going to focus essentially on a 14-day time period prior to the start of the forecast. In this 14 days, the biggest thing moving in the Gulf of Mexico is the loop current. So our EOF modes are going to be related to the variability of the loop current, our primary target. Okay? So once we've identified the spatial modes as the EOF, okay, each one of these will be multiplied by an uncertain amplitude, psi k. The series that I have here is essentially showing the addition of 4 modes, perturbing 4 modes of that EOF decompositions with uncertain amplitudes. Okay? So these are my uncertain input variables, 4 amplitudes of the EOF modes. And then I add them to my unperturbed case. That's, in a way, you can think of it as your control. Okay? And then you can launch the simulations. Okay? So the EOFs are coming essentially from a previous forecast that has actually essentially data assimilated. So data is indirectly put into this the construction of these EOF modes. Okay. The thing that I would like to stress is that from a practitioner point of view, all the head scratching is not in the polynomial chaos. The head scratching is here. How do I perturb? Okay. And this is an issue that is pervasive to all ensemble methods. How do I perturb my ensemble? How do I generate my ensembles? And the issues for polynomial chaos is a little bit elevated because you're building linkages. You keep track of the relationship between the input uncertainty and your output. So you have to be very clear about this. In my mind, it keeps you honest the entire time, okay, of what you are perturbing, okay, and its effect on the output downstream. And so let's examine these modes a little bit. And what you're looking at are the spatial patterns of the first and second mode and the sea surface height. Okay? And so what you're looking at here is essentially strengthening of the frontal eddy that is working on detaching the loop current or weakening it. And so the biggest signature are in the loop current regions. Okay? And the first mode accounts for about 35% of the variance. When you add the second mode, it's about 50% of the variance. If I include more modes, okay, I make my parameter space larger. My series has to, the dimension of the space is larger, and the sampling requirements goes up. So as a first experiment, I'm going to just do the first two modes. And in a later experiments, I'm going to add the next four modes that get me up to about 70% of the variability. Okay. And so by using this technique, I was able to localize the perturbation about a dynamical process that I'm interested in. I don't know if this generalizes to all situations, but it works in the Gulf of Mexico. Okay. And these are multivariate EOFs, and this is a slice through the frontal eddy. And what you've done for your perturbations is you have, like, for example, produced a cooling of about almost 2 degrees and warming on the western side of the loop current. Okay, a warming of about 2 degrees as well. So these are perturbations that affect all variables in the models. We did the same thing for the winds, essentially. We took the winds that were available that we were going to force the model with, and we perturbed them similarly. We identified their EOFs and perturbed them. So the input uncertainties with the wind are also the amplitude of these modes. Okay. So again, essentially we have an 8-dimensional space, and we're assuming all these parameters to be independent and uniformly distributed. Okay. And the wind perturbation here are the first 4 modes, and they're mostly associated with variability of the Atlantic high pressure system. You either have winds coming from the northeast or northwest or southeast. Okay. All right. So these are the 2 UQ experiments that we're going to perform. I'm going to talk about today's. And experiment 1 is really, it was our starting point, so it was the simple setting of just turning off the variability in the wind and just keeping the variability in the initial conditions, just 2 modes, okay? And so because the dimension of the problem was small, we could use the Galerkin projection very efficiently and Gauss quadrature. And we use 6-degree polynomials, so that means you need quadrature in, you need 7 samples in each direction for a total of 49 quadrature points, okay? And so we ran the model for about 60 days, but the series was reliable only for about 30 days, okay? So whatever the series is giving me after day 30 is inadequate. I either have to enrich it, increase the ensemble size, or not use it after day 30. That's the beauty of actually having a polynomial chaos. you know whether the sample is telling you something about how your input and the outputs are related, okay? Whether you have sampled the space enough. For the second experiment, it was essentially much larger, and we needed to use the basis function were also Legendre polynomials, and we used basis pursuit denoising in order to sample the space. Otherwise, we would have needed millions of samples to do it with this traditional technique. Clearly impossible. But with latent hypercube sampling and compressed sensing, we had a good series using an 800-member ensemble for about 30 days. Okay. So let me show you essentially the quadrature points, the samples. So you're looking at the uncertain space, Xi1 and Xi2. Okay. This is my unperturbed run here, right in the middle. If I add positive contributions, I'm here. I'm adding full positive directions for mode 1 and mode 2. If I multiply it by -1, I'm putting the perturbation in the other directions. Okay? And so I'm going to show you these three extremes. Okay? And we had to sample on the red stars. And the black stars are essentially independent validation points. I'm going to use them to make sure that my series is reliable. Okay? So it turns out that examining the runs at these 3 points is very revealing, because it also confirms that our perturbations are really affecting the strength of the loop current and of the frontal eddy. Okay? So this is a little bit complicated to look at. The vertical axis essentially is a time axis, day 1, 20, 40, 60. And this is, the middle is the unperturbed run. Okay? This is the most negative perturbation, lower left corner, the most positive perturbation, the upper right corner, and this is the polynomial chaos mean. Okay? And so at the first day, the ocean state hasn't really moved that much, so you're really looking at the initial perturbations. And if you look at the unperturbed state, here's your frontal eddy, here's your extended loop current. And when you added the negative perturbation, the frontal eddy has kind of weakened substantially. So this corresponds to weakening the frontal eddy, where the positive perturbation serves to strengthen the frontal eddy. Okay? And you can see the effect of the strengthening and weakening and the time evolution, where when you weaken it, the loop current remains attached for a much longer period of time, whereas in the unperturbed simulation, it detaches sometimes around between day 20 and 40, right? Whereas for the most positive perturbation, the cleavage starts almost at day 20. By day 40, you already have a well-detached system and an interacted system. Okay. All right. Any question up to this point? Everything's clear? Okay. All right. So we were pretty happy with that. There was essentially a good story, and the whole science really was in the design of the perturbation. And the solution we came up with works for our system, but the practice in other places is different. You're looking at singular vectors, the most unstable vectors, or breadth vectors. And these are hard to compute. This turned out to be easy to compute. Okay. It's not the optimal, but it works for our case. So let's look a little bit at what we can learn from these things. I'm not going to show a lot from experiment 1, just a few pictures. So what you're looking at, essentially, we're using the validation point to assess whether the difference between the surrogate and an actual model run is small or large. Okay? And so we essentially looking at the root mean square error here, and its evolution in time. And on the right panel, you're looking at the standard deviation of the system. So it's pretty clear that the surrogate is reliable all the way to about day 30. It's not in this panel, but the problems for the error start showing up at day 40, also in the loop current region. It's about an error of about 12 centimeters in sea surface height. Okay. The standard deviation grows as time goes by. And you see a spot also like in the place where the loop current is going to separate, and it grows as time goes on. But if you look at the two different ratios, you realize that essentially your standard deviation is about 24 centimeters in the loop current region. It peaks at about 32, and it's a substantial portion of the error in the surrogate. So at this point, at day 40, you're missing, your surrogate is not doing a good job of representing the response surface. And so you wouldn't trust this. There's missing variability here. You need much more samples to characterize it. Okay. All right. And so if you take, since the standard deviation is available, you can compare it to a climatological standard deviations and decide whether you have lost predictability in the system or not, right? If the standard deviation of the climatology is narrower than the standard deviation of your ensemble, you've lost predictability, right? You might as well choose from the climatology. That's one measure of predictability, okay, one easy measure. And it looks like it starts peaking in the loop current regions around day 20, right? In other places, you still have predictability. And so we think that the predictability in the loop current system is about 3 to 4 weeks, essentially. You know, day 40, the reliability of the surrogate and what you infer from it is in doubt. Okay.